Okay, let's get some end of the week practice in, covering this FE type questions covering water distribution systems. So what I want you to do is pause the video, read that problem statement slowly, think of what you're given, denote what you want to find, then do your best to arrive at a final answer by struggling through a solution. So this is the best way to learn, making mistakes, seeing where you get stuck, and if you get the final answer correct, that's excellent. If you don't, that's great too. You're learning from your mistakes. You're learning from where you got stuck, why you got stuck, and you're just trying to focus on your weaknesses and learn from that. This is the best way to learn. Now let me show you how I would do this. So we're told water enters the distribution system at a flow rate of 10 CFS as shown. The Hazen-Williams coefficient, diameter, and the length of each pipe is given. The flow rate in CFS in pipe 1 is most nearly what? So we're given a water distribution system, and the flow rate that comes in is 10 CFS, cubic feet per second. CFS, C for cubic, feet, second, cubic feet per second. That comes in into this water distribution system, and some flow comes out, and we'll talk about that as we continue. So we know the Hazen-Williams coefficient, diameter, and the length of each pipe is given. So the C value is always our Hazen-Williams coefficient. So you have to know that anything with C, Hazen-Williams, the friction factor is going to be the Darcy. The italics F is Darcy friction coefficient. We're looking at the Hazen-Williams in this case. The diameter is given, that's D for each pipe, and the length of each pipe is also given. And conveniently, notice something. The length here is the same as this length. So that length is not going to be that important when we continue, but just note they're also giving us the length. It may change on different problems. In this case, they're both the same. So we know we want to find the flow rate. So what I'm going to do is write what we want to find on the side. The goal is to find that flow rate in pipe 1. Be very careful. We're focused on this pipe, the top one, which is pipe 1. So we'll say pipe number 1. This one, not 2. We can find 2, but we want to find 1 in this one. And we want the units going to be in cubic feet per second. That's going to be CFS for that flow rate Q. So the way I'll denote it as what I want to find, I'll call it Q1. Let's call it Q1. And we know what we're given essentially is this stuff here. So basically everything we need to use is given in the diagram. And that 10 CFS, let's just call it Q. Let's just denote it. This is the total flow rate that goes into this very simple distribution system with 2 pipes. So that's what we're given, that Q and all the other variables. So now what we're going to do is go into that solution. So the first thing that we should think about is the flow, like how the water is going to flow. So you have to imagine this like this. So we know 10 CFS is what comes in into essentially the distribution system. The majority of it is going to be this middle part. That's what we need to focus on. So it comes in, and we know some flow will go this way and some flow will go this way. And that happens at this node. It's that junction, or we call it a node in a distribution system. So we know the flow comes in, some flow goes this way, some flow goes that way. And what I'm going to do is denote these by colors, just when we're learning this. We know the flow that goes this way, we can use red, and we'll call it Q1 for pipe 1. So that makes sense. We'll call that Q1. And the flow that goes this way, I'm going to call it Q2. This would be Q2. And notice how both of these, it's going to split here. This is Q1, this is Q2, then they combine again. So note, this is still Q2, this one, and this is still Q1. It goes back down. Then they combine again, and we get an output. So now I want you to think about this. That output would be what? Q1 plus Q2. That's going to be what comes out. In fact, it's just going to be the 10 CFS, because that 10 CFS split here. Then when we come back here, it's going to, again, combine. So split here, and here it combines, and it comes out. So you just have to know that what comes in is what's going to come out at this node, at the node at the end. So it's going to be 10 CFS as well. And that's all continuity. And we'll use that as well to actually solve this question. But I just wanted to give an overall picture of what we're given now. So now, let's actually solve this. So we know the first thing that we have to realize is we have a certain type of setup in the distribution system, and we know it's going to be parallel. It's called parallel, where the pipes essentially are parallel to each other. So in this case, this is a parallel setup, and if we refer to the FE Handbook, we can get some important information about these parallel setups, specifically when we have the friction head loss. The head loss due to friction, or the major head loss we have in pipes. So what I'm going to do is go into the fluid section, and I can just use the arrows in my PDF. So I'll just do it this way, and I won't do Control F, but I'm going to find it under multi-path pipeline problems. So you can do Control F and find that, but I just like using the bookmarks, fluids, find that. And let me zoom in here using the zoom in button. Let me use the hand just to move around, similar to the FE. But we have what we have here, right? So we know in this one, this is actually multi-path pipeline problems for parallel configuration, where you have a pipe on top. In this case, this one's going to be pipeline B. The pipe B is going to be parallel to pipe A. So it's a parallel setup. And what's special about this, it says in pipes in parallel, the head loss is the same in each pipe. So you just have to always know that the head loss will always be the same in each pipe. So the head loss in pipe A is the same as the head loss in pipe B. So that is something that we always have to know for parallel pipes. Parallel pipes. So this is a good page to know in case, let's say, they give you the friction factor, the Darcy friction factor. But in this case, we're going to focus on the Hazen-Williams equation in terms of the head loss. And I'll show that in the PDF of the handbook as well. But let's go back into our solution and write that. Since we have a parallel configuration, the head loss in 1 must equal to the head loss in 2. That's number 1. We have to denote that. So we know number 1 will say the head loss due to flow in pipe 1 is going to equal to the head loss due to flow in pipe 2. So that's the first thing. Now the question is, the head loss due to flow on that page, if we look, is based on that friction factor, which is for Darcy. In this case, we have the C value. So this will not help us. We cannot apply the Darcy equation. But we know the head loss idea, they're the same, is still true. So what we can do is actually do Control F. And let me show you this. If you're given anything with the Hazen-Williams coefficient, and we're talking about distribution system or head loss or any of that stuff, let's just search Hazen. But what I'm going to actually do first is go into civil engineering. Then I'm going to try to find it. And let me see what it does. And it should give us a page where we have all the Hazen-Williams equations. So let me go. And for the Hazen, so this one's going to be the Hazen-Williams equation. We're not going to use that, but it's directly under that. Let me go to the next page. In fact, it's going to be this one. So we're here. So this is what we're going to focus on. This is the head loss expressed in units of feet. So the head we lose in terms of feet. And this is the big equation we're going to have to use. And notice how it uses that C value, the Hazen-Williams coefficient. So we're going to use this to actually solve this question. So what I'm going to do is go back and denote that for each pipe. For pipe 1 and pipe 2. So what we're going to say, how I have it in my solution, is 4.73 is going to be the first number. And we take that times L1. We divide by the C value C1, the Hazen-Williams coefficient, and we raise that to the power of 1.852. So that's going to be that. Then we take D1 and we take that raised to the power of 4.87. And now we take all of that. Note, when we go back here, it says times the Q value. The Q value for pipe 1, pipeline 1. So if I go back here, the Q value is going to be the just Q1. And let me stick with my colors. We denoted that in red, Q1, and we raise that to the power of 1.852. And we do the same thing for pipe 2. So this one, 4.73, we take that times L2, the bottom one. We're focused on this one. Then we take C2, 1.852, and we take that times D2, and we raise that to the 4.87. And we take that times the Q2, we know it's going to be this in red, in this color pink, and we take that to 1.852. So that's going to be that. So this is the big equation we're going to use, and this will help us arrive at a value for Q1. So now we notice this equation though, there's a problem. This is one equation, two unknowns. So we're stuck. One equation, two unknowns. Remember, for each equation, you can only have one unknown to actually find that unknown. So if you had one equation, one unknown, it's good. The unknown, let's say, is X or Q, we can use it, we can solve it. But in this case, we have one equation, two unknowns, we can't really work with it. What we can do, though, is use another property about distribution systems and conclude continuity, something that's very important for these systems. So if you had to look at this node, this junction, the flow comes in and the flow comes out. So always at any node or junction in a distribution system, whatever comes in has to come out. What comes in has to come out. So what we can say based on continuity, so we'll say continuity, we will say that in must equal to out. So we'll say flow in equals to flow out. And this is true at the nodes, at the junction, at node. So we will say the flow in. If you go above, let's focus on this node, or you can use the node here, the one downstream at this side, but let's just do this one. So what comes in is the 10 CFS. So what we can simply say, it's going to be the 10 CFS cubic feet per second is going to equal to what comes out. The flow out is Q1 and Q2. Both of these combined is the one that comes out that node. So it's going to be Q1 plus our Q2. So now this is going to be important because we can actually solve for Q2 in terms of Q1. So if we solve for Q2, this one, in terms of Q1, we can plug it in here and we get one equation, one unknown. So the way this would look is Q2 is going to equal to the 10 CFS, 10 cubic feet per second, and we do that minus Q1. Minus Q1. So that is going to be the equation for Q2 in terms of Q1. So what we can do is actually take this. So I'm going to show it for us. We can take this here and we're going to go above and plug it in here. And then we get that 10 we know. Then we get this whole equation and one unknown, and we can solve for Q1, which is what we essentially want to find at the end, Q1. So now for step 3, I'm going to start plugging numbers in. Let me start plugging numbers in. So we know what's special about this one. We said in the initial problem statement, notice the lengths are the same. So we know that L1 in this case is going to equal to L2. So we can just drop these out of the equation. They're the same. So you can put them or drop them. You'll still get the same answer. But we know L1 and L2 essentially cancel. They're the same on the equation. So we know they're the same. They just cancel. So then what I'm going to do is reduce this and start plugging numbers in. So we will say it's going to be 4.73 divided by, and we take that divided by 100. We raise that to the power of 1.852. And we know that 100 is which one? It's going to be the coefficient for pipe 1. The left side here of the equal sign is the head loss for pipe 1. Then we take that to the diameter. So what's the diameter? 4 inches. 4 inches for pipe 1, but you have to be careful. We want the answer in flowrate cubic feet per second. So those units of inches have to be converted to feet. So we can simply divide by 12. So taking that 4 divided by 12 gives us feet. So 4 divided by 12, because we know there's 12 inches in 1 foot. So we take the 4 divided by 12. So what we will do for this is take the 4 inches divided by 12, and this converts it to feet, doing this. But we have to raise that to the power of 4.87. So that's going to be that part. So what we just did is this. Then we take that times Q1 to the 1.852. And Q1 is actually what we want to find. So we take that Q1 to the power 1.852. So then this equals to what we have on the right side. Same idea. So doing the same thing, we take 4.73 divided by the Hazen-Williams for which one, pipe 2, is going to be the 140. Diameter is going to be 6. So if we go down, we would put that 140 and 6. So it's going to be 140 for this, raised to the power of 1.852. And we take that 6 divided by 12, because we want to convert that to feet. And we raise that to the power of 4.87. So that's going to be that part. Then we know, let me move this a little to the left. So if I take this, just move it a little here. And we can plug in what we have at the very end. And we have to realize what we did from here, from continuity, we got a relationship. Q2 is going to be 10 minus Q1. So we're going to put that for Q2 to get everything in terms of Q1. So what I'm going to do is put that in here. But we have to raise it to that power. Be careful. Do not forget that. So we have to do this. So we will say it's going to be 10 cubic feet per second. So let me denote the units. And we do minus Q1. And all of this is still raised to the power. It's the same power as this, so it's going to be 1.852. Now we have one equation, one unknown. So let's start plugging stuff in the calculator. So let me show you how I would do this. So I know here what I'm going to do is actually take this and reduce it, take this and reduce it. So we're going to get some values for these. I'm going to do that first. So let me do that in the calculator. So we will take the 4.73 divided by what we have as 100, and we raise that to the power of how much? 1.852. Okay, that's done. So we will take that, then we take the 4 divided by 12, and we raise that to the power of 4.87. So that's going to be that part. And we do nothing to this. We're going to keep going and fix that. So 0.197 is going to be this part. So the way I would show this is 0.197 would be only this part, but that Q1 is still there. That's unknown. 1.852. Now let's do this side. So what we would do is the same idea. So what's convenient about this is you can go above, grab this, and what I'm going to change is going to be the 4. That becomes a 6. So 6 divided by 12. And what I can do is go here and change that 100 to 140. So we have that and enter, and we get that value. So we get about 0.0147, and that's this part, and this doesn't change. It's still gonna be that 10 CFS, 10 minus the Q1, and we raise that still to the power of 1.852. So now we have this one equation, one unknown. What we can do now is actually use the solver. Let me use the calculator solver, because I don't want to do that algebra. It's doable, but the solver is just going to save me time. So let me do that, and what I'm going to do is going to be second number solve, clear the left, clear the right, and what we have on the left side of the equal sign is 0.197, and that's going to be multiplied by Q, which is the unknown X. Think of Q as the unknown. We raise that to the power 1.852, and that's going to be the left side. Then we have the right side, and that's going to be 0.0147. We take that 10 minus the X is the Q, the unknown Q1. We raise that to the power of 1.852. And that is one equation, one unknown. The unknown is X in the calculator, which is our Q1. So now enter, you'll solve for X, let it solve, and we should get that value. We should get that Q value, and we get it to be 1.97 is the Q value, which is essentially our Q1. So Q1 equals to 1.97 cubic feet per second. So this would be our answer. And if we go above, we would pick C for that one. I hope you found this practice problem helpful. Don't forget to keep putting in that study time. Always take your breaks, and I'll see you in the next video.